Our goal is to understand how variation in one variable might be caused by variation in other variables. But what we want to do in that process is to understand how much each variable is contributing to the variation of the response variable. That is, we really would like to understand the effect that one variable has on another. And the size of that effect, called effect size, can be indexed with various statistics. These are estimates of the effect size, estimates because we're using a set of data that can vary from sample to sample, and we're wanting to estimate the true effect, but that effect, of course, is going to show up differently for different samples, so we're just estimating the actual effect based upon the data that we have in hand. So let's look at estimates of effect size. The magnitude of the effect that one variable has on another is the effect size, and in the simple linear regression situation, there are two primary effect size estimates we can use. One is the slope of the regression line. That tells us the average effect of the explanatory variable on the response variable. Remember, the way that you interpret slope is that it tells you for every unit change in the explanatory variable how much average change you expect to get in the response variable. And the coefficient of determination, which we've talked about, that's an estimate of the proportional reduction in error obtained with the explanatory variable. So it's a measure of the reliability of prediction using this variable, or in other words, it tells us how good our model is. The coefficient of determination we saw was r squared, but we can understand it even better by relating it to the sums of squares that we looked at in the last video. The sum of squares total is the error of prediction when the explanatory variable is not used. That is, we're just using the mean as the index of our response variable, and deviation from the mean would be considered the residual or the error. And the more variance we have, the larger those deviations from the mean are. The sum of squares error is the error prediction. That's the sum of squares based upon our residuals when the explanatory variable is used. The coefficient of determination is the proportion of the total sum of squares that can be explained by the model. So r squared is actually an indication of the proportion of the total deviations about the mean squared that can be accounted for by the explanatory variable. That is our model that we're using to predict the response from that explanatory variable. Now here I've shown that the sum of squares model, we know that from the previous videos, is that it's just the sum of squares total minus sum of squares of error, the residual. So these are just two ways of expressing the same thing. But interestingly enough, squaring the correlation, which is what we did in an initial video in order to obtain the coefficient of determination, this really provides us some concrete meaning. What proportion of that total sums of squares can I account for by including that explanatory variable? So when we looked back at our example where we earlier on calculated the coefficient of determination to be 0.68, that tells us that 68% of the total sums of squares can be accounted for by the model. So I believe we have those up here. We calculated these from a previous video. Yes, we actually created an ANOVA table, and I still have the total sitting down here of 53637. So if I were to take the model sums of squares, which is 36464, that is the 36464, that I'm finding that number right here in the ANOVA table, the analysis of variance table, 36464. And if I were to divide that into the 53637, we end up with 0.68. That is, we're confirming that this is the same as taking the square of the correlation of those two variables. Two different ways to get the coefficient of determination, but the sums of squares method maybe not as easy for calculation as the correlation squared, but it actually helps us with our understanding of what that means. So we have yet to turn our attention to inference, and I think I'm going to make sure that we've done all the descriptive and graphical things that we need to before we turn our attention to inference. Let's see. No, here's something right here. I never talked about this portion. So when we ran our model and got a summary of our model, one of the first things that appeared was this little summary, 5-number summary of the residuals. That, in fact, is something that can help us understand our data, because we know the smaller the residuals are, the better the model's doing. But small is a relative term. This gives us actually absolute values. So the smallest residual that we have, the minimum, is minus 3.8. Now remember, we're predicting mortality from latitude. So what that tells us is that there is one case, there is one state in which if you were to predict the mortality, you actually would be under predicting it based upon the latitude by about 39. And on the other side of the spectrum, there is one state in which you predict the latitude. Now, this one I think I might have said backwards. Did I say under predicting? You would be predicting a mortality, and the actual mortality would be under what you predicted. So you would be predicting too much. Here is a case in which our maximum residual observed minus the predicted, our observed minus predicted is a positive 44, meaning the observed is 44 more than we predicted. So there's where we're under predicting. And then we have the median and the first quartile and the third quartile. Notice that the median is about 1. That means that right there in the middle, that we are predicting about off by about 1. Now, that's not that amazing to me. Let's remember that we have the residuals here in our skin details. And if I were to take the mean of the residuals in the skin details, we end up getting 0. Now, R is doing a calculation in which it's got decimal points to a finite place. So that's why you're getting this funny looking number. But remember, e to the negative 15 means 10 to the negative 15 means move that decimal point 15 places to the left, 0.00000, and so on. So it's essentially 0. That is always the case. The mean of the residuals will always be 0. That's just a mathematical fact that we could prove, that the mean of the residuals will always be 0. Just like when we take the mean of deviations without squaring them, that will always be 0 as well. Because if you take the mean of deviations from the mean, if you were to take the deviations from the mean and then add them all up, you would have the negatives offset the positives. The mean is actually what we would think of in physics as the center of gravity. And so because it's the center of gravity, you automatically have 0. Similarly, the residuals in our model will always have a mean of 0. So this just provides us some absolute sense. We already know that the residuals are relatively small. Why? Because the model was strong. But relatively small, now we can actually put in values what that means. We have a first quartile of minus 13, a third quartile of 12, and that's pretty compact. Okay, that first quartile, that's the inner quartile range, that middle 50% has everything within around 12 or 13 points. 12 or 13 deaths per, 10 million? 12 or 13 deaths per 10 million. Our prediction is within that of observed. So there is something to learn about the model and about the data by looking at those residuals. Okay, we've already talked about the intercept. We've already talked about the slope. We've talked about the correlation. We've talked about the coefficient of determination. We've talked about the sums of squares. So I think we have pretty much covered it in terms of graphically the scatter plot, graphically the line going through the points, and in terms of descriptive statistics. So why don't I go ahead and end this video here, and then we shall talk about inference and making inferences, which is important because we're dealing with a sample of data and we don't know how stable those estimates we're creating are. And we want to know if we have good stability of estimates so that when we provide these statistics, these indices, we don't expect if someone else went out and collected another data set that they would get drastically different numbers. Especially if they're collecting data the same size as ours, we would like to know that they're similar numbers to what we're getting. It may be that we have too small of a sample to have a good stability, or it may be that we have so much variation in our data that we can have a lot of instability. So we need to be able to make inferences. How well can I generalize this outside of this study? And we'll take on that topic in the next video.